China's AI glass is sold out until 2027. At least that's what recent industry reports suggest. Think about that for a second. Not GPUs, not AI chips, not the world's most advanced lithography machines. Glass, a material so ordinary that most of us walk past it every single day without giving it a second thought, has suddenly become one of the most valuable resources in artificial intelligence. And here's the part that caught my attention. NVIDIA, the company leading the AI revolution, may need up to 36 times more optical fiber than traditional computing infrastructure as it builds ever larger AI clusters. That means the race to dominate artificial intelligence may no longer be decided only by who designs the fastest processor. It may also be decided by who can manufacture enough ultra-pure glass to connect those processors together. By the end of this video, you'll understand why a single strand of glass has quietly become one of the most strategic materials in computing, why demand is exploding faster than factories can expand, why China suddenly occupies the center of this story, and why the next AI bottleneck may not be inside the chip at all. It may be hiding in the cable connecting one GPU to another. Let's get into it. To understand why AI glass has suddenly become one of the hottest commodities in technology, you have to stop thinking about artificial intelligence the way most headlines encourage us to. Every day we're told the future belongs to whoever builds the fastest GPU, the smallest transistor, or the most powerful AI model. We hear about trillion-parameter systems, next-generation chips, and billion-dollar semiconductor factories. Those stories are important, but they leave out something far more fundamental. None of those breakthroughs matter if the chips cannot communicate with one another quickly enough. The biggest AI systems on Earth don't rely on a single processor doing all the work. They rely on thousands, sometimes tens of thousands, of processors working together as one enormous machine. And that cooperation only happens because every processor is constantly exchanging unimaginable amounts of information with every other processor. If that communication slows down by even a small amount, and the world's most advanced AI chips are forced to sit idle, waiting for data instead of performing calculations, suddenly the expensive silicon isn't the bottleneck. The connection between the silicon is. That's where glass enters the story. When most people hear the word glass, they picture windows, smartphone screens, or perhaps laboratory equipment. Very few imagine one of the most strategic materials in modern computing. But the glass used inside AI infrastructure isn't ordinary glass. It's an ultra-pure optical material capable of guiding pulses of light across enormous distances while losing almost none of the information being transmitted. Inside every optical fiber is a glass core, so pure that a beam of light can travel for kilometers while remaining remarkably intact. Those tiny pulses of light have become the language of artificial intelligence. Every instruction, every model update, every memory request, every synchronization signal races through these strands at nearly the speed of light. Without them, the AI revolution simply doesn't function. Here's where the scale becomes difficult to comprehend. Traditional data centers mostly handle traffic flowing between users and servers. Someone watches a movie, opens an email, or visits a website. Information enters the data center, reaches the correct machine, and leaves again. Engineers call this north-south traffic. AI data centers operate very differently. Most of the traffic never leaves the building. Instead, thousands of GPUs constantly exchange information with one another while training massive neural networks. This is known as east-west traffic, and it grows at an astonishing rate as clusters become larger. Every processor finishes part of a calculation, immediately shares the result with countless neighboring processors, receives updated information in return, and begins the next step almost instantly. This cycle repeats millions upon millions of times throughout a single training run. Imagine asking 10,000 musicians to perform one perfectly synchronized symphony. Every performer must hear every cue at exactly the right moment. If one section falls behind by even a fraction of a second, and the entire performance begins drifting apart. AI clusters behave in much the same way. Every GPU may be extraordinarily fast, but if communication slows, everyone waits. Expensive processors consuming enormous amounts of electricity suddenly become incredibly efficient at doing nothing. That idle time is one of the costliest inefficiencies in modern computing. This explains why NVIDIA, despite dominating AI accelerators, has become increasingly focused on networking rather than processors alone. Building faster GPUs solves only part of the problem. The other challenge is ensuring those GPUs communicate without delay. As clusters continue expanding from hundreds of accelerators into thousands and eventually tens of thousands, the communication network becomes just as critical as the chips themselves. It's a fascinating shift because the spotlight is quietly moved away from silicon toward infrastructure. If you've been enjoying these deeper technology stories, I'd love to know where you're watching from. It's honestly one of my favorite parts of making these videos because the comments often remind me that people from every corner of the world are just as curious about how these technologies actually work beneath the headlines. Now consider what happens when every new AI generation demands dramatically more connectivity than the last. Industry analysts estimate that advanced AI installations may require dozens of times more optical fiber than traditional CPU-based computing environments. Corning, one of the world's leading optical technology companies, has noted that certain NVIDIA-based AI systems already consume many times more fiber connections than conventional cloud infrastructure. Those aren't small increases, they're exponential changes in demand, and demand creates pressure. Recent reports suggest several major Chinese optical fiber manufacturers have order books extending well into 2027 for certain high-performance products. That doesn't mean the world has literally run out of fiber optic cable. Homes won't suddenly lose internet access because AI consumed all the glass. The reality is more nuanced, and specialized products used inside advanced AI facilities, high density, low loss, bend-resistant optical fiber designed specifically for massive computing clusters are experiencing extraordinary demand. Manufacturing schedules are becoming increasingly crowded because factories simply cannot expand overnight. This is where many people misunderstand the challenge. Making optical fiber sounds deceptively simple. Melt some glass, pull it into a thin strand, and you're finished. In reality, producing semiconductor-grade optical fiber is one of the most demanding manufacturing processes in existence. Everything begins with what's called a preform, essentially a large cylinder made from exceptionally pure engineered glass. The chemical composition must be controlled with astonishing precision because even microscopic impurities scatter light and reduce performance. After the preform is manufactured, it's carefully heated while machines draw it into an incredibly thin strand, reducing something weighing hundreds of kilograms into thousands of kilometers of fiber, thinner than a human hair. And that drawing process cannot vary by more than tiny fractions of a millimeter. Protective coatings must be applied immediately before microscopic flaws appear. Every meter undergoes testing, every spool requires inspection. Only after passing multiple quality checks does it become part of the cables connecting AI servers around the world. Here's the catch. Building another fiber factory isn't like adding another assembly line inside an existing warehouse. New preform facilities require specialized equipment, carefully controlled manufacturing environments, highly trained engineers, and years of construction before reaching full production. Industry experts often estimate that meaningful new capacity can take well over a year, and sometimes considerably longer, to become operational. Meanwhile, AI demand can double in a matter of months, and that's why the current imbalance exists. Demand grows like software. Supply grows like heavy industry. One moves at internet speed, the other moves at factory speed. And no matter how urgently companies need more glass, they can't compress years of industrial expansion into a few quarters. If this part of the story surprises you, consider sharing this video with someone who follows AI closely. Most conversations revolve around GPUs, models, or semiconductor manufacturing. But very few people realize just how essential these seemingly ordinary strands of glass have become. Sometimes the most important technological breakthroughs aren't the glamorous ones. They're the invisible components, quietly making everything else possible. The remarkable thing is that this shortage didn't appear because manufacturers failed. It appeared because artificial intelligence expanded far faster than almost anyone predicted. Infrastructure that once looked excessive suddenly looks inadequate. Capacity that once struggled with oversupply now finds itself booked months or even years ahead. And that's setting the stage for one of the most fascinating industrial races unfolding anywhere in technology today. The really interesting part of this story begins once you stop thinking about glass as just another material and start thinking about it as infrastructure. That's the shift many people miss for decades. The semiconductor industry treated the substrate as something important but secondary. The spotlight always belonged to the transistor, the lithography machine, or the newest process node. Meanwhile, the foundation underneath every advanced chip quietly became one of the biggest engineering bottlenecks in modern computing. AI changed that almost overnight. Every new generation of accelerators demanded larger packages, tighter interconnects, and dramatically higher power densities. And the chip itself kept improving, but the material supporting it struggled to keep pace. Engineers found themselves fighting tiny distortions caused by heat, mechanical stress, and signal interference that simply didn't matter 10 years ago. Those problems don't generate flashy headlines, yet they can determine whether a billion-dollar AI system performs reliably or develops failures after months of operation. That's why companies across the industry are suddenly racing toward glass. It isn't because glass is fashionable, it's because the old foundation is reaching limits that become harder to ignore every code year. If you've stayed with me this far, I'd genuinely love to know what you think. These conversations have become one of my favorite parts of making these videos because so many viewers work in engineering, manufacturing, software, and research. Every time I read the comments, I learn something new. So if this topic fascinates you even half as much as it fascinates me, leave your perspective below. There are thousands of incredibly smart people watching these videos together, and that's something I never take for granted. And this also explains why the phrase "sold out until 2027" deserves careful interpretation. It doesn't necessarily mean every factory has completely exhausted every piece of glass it can produce. And what it often reflects is something far more important: qualified production capacity. Semiconductor manufacturers don't simply buy raw materials like ordering office supplies. Every supplier, every process, every production line must be validated through months or even years of testing. Once that qualification happens, customers reserve enormous portions of future production because redesigning a packaging platform later is extraordinarily expensive. In other words, when future capacity gets committed years in advance, competitors cannot simply arrive with more money and immediately buy their way into the supply chain. The queue itself becomes a strategic advantage. Now think about NVIDIA's position. The company continues designing increasingly powerful AI processors that consume more electricity, generate more heat, and integrate more chiplets than previous generations. Every one of those trends increases demand for advanced packaging materials capable of maintaining mechanical stability and electrical integrity. If future AI systems truly require dramatically more advanced substrate area than today's hardware, and then securing sufficient quantities becomes just as important as designing the processor itself. The fastest chip in the world accomplishes very little if production cannot scale, because supporting materials remain constrained. That's why discussions surrounding advanced packaging have moved from engineering departments into executive boardrooms. They're no longer technical footnotes, they're strategic priorities. One lesson keeps repeating throughout technology history. The companies that dominate one generation often assume the next generation will reward exactly the same strengths. Sometimes they're right. Sometimes the entire competitive landscape shifts underneath them. The smartphone revolution rewarded companies that mastered software ecosystems. Cloud computing rewarded those who invested early in massive data centers. Artificial intelligence rewarded whoever could manufacture advanced accelerators at unprecedented scale. The next phase may reward something different altogether. Whoever controls the packaging technologies that allow those accelerators to keep growing, and that's a subtle shift, but potentially an enormous one. Here's something I find fascinating. Many technological revolutions don't happen because someone invents an entirely new law of physics. They happen because someone solves an overlooked engineering problem that everyone else considered boring. Electricity transformed society not merely because generators improved, but because transmission networks expanded. Aviation advanced because materials improved alongside engines. Computing accelerated because manufacturing processes matured alongside transistor design, and the glamorous breakthrough usually receives the headlines while the supporting technologies quietly determine who actually wins. Glass substrates may become one of those hidden enablers. If that happens, historians may eventually look back and realize the biggest story wasn't simply AI chips, it was the material underneath them. And that's why supply chains matter so much. They don't simply determine prices, they determine timelines. Every month spent qualifying new suppliers and delays product launches. Every manufacturing bottleneck ripples outward through data centers, cloud providers, AI startups, enterprise customers, and eventually consumers. Modern technology is interconnected in ways that weren't true 20 years ago. A shortage in one specialized material can influence investment decisions halfway around the world. That's difficult to appreciate until you step back and look at the entire ecosystem instead of a single company. If you're enjoying these deeper explanations, consider subscribing, not because I want another number on a screen, but because I genuinely enjoy exploring stories like this with people who appreciate looking beneath the headlines. There are thousands of technology news articles published every week, yet very few spend time explaining why these developments actually matter. If that's the kind of conversation you enjoy, I'd be happy to have you here for the next one. Of course, it's equally important not to exaggerate what's happening. Glass substrates remain extraordinarily difficult to manufacture. Yield challenges haven't magically disappeared. Through glass, vias remain complex. Thermal reliability must still be validated across years of operation. Companies outside China, including Intel, Samsung, Corning, TSMC, and numerous packaging specialists, continue investing heavily in competing approaches. And this is not a finished race with a predetermined winner. Anyone claiming otherwise is probably simplifying an incredibly complicated industry. Technology leadership rarely changes overnight. It shifts through thousands of engineering improvements accumulated over many years. Still, momentum matters. Once production reaches sufficient scale, experience compounds. Every manufacturing run generates data. Every defect teaches engineers something new. Every improvement increases yields, lowers costs, shortens delivery times, and strengthens customer confidence. Those advantages reinforce one another in ways that become difficult for competitors to replicate. That's exactly how TSMC established its leadership over decades. It wasn't one miracle invention, it was relentless manufacturing excellence, compounded year after year. Whoever achieves that same compounding effect in advanced packaging could enjoy a remarkably similar advantage. Perhaps that's the biggest lesson hidden inside this entire story. We often imagine technology races as dramatic competitions between revolutionary inventions. Reality usually looks different. Progress belongs to whoever solves hundreds of difficult problems that most people never notice. Better materials, better factories, better yields, better logistics, better quality control. None of those sound exciting individually, and together they reshape industries. Personally, I think that's what makes semiconductor manufacturing so fascinating. Behind every AI breakthrough sits an entire universe of precision engineering that almost nobody sees. The world's attention naturally focuses on chatbots, robots, autonomous vehicles, and massive language models. Meanwhile, somewhere inside a factory, engineers are spending years learning how to drill microscopic holes through glass, reduce thermal expansion by tiny fractions, or eliminate defects measured in nanometers. Those invisible achievements make everything else possible. Before we wrap up, I'd love to leave you with one question because I honestly don't think there's a simple answer. When a technological advantage depends less on scientific discovery and more on manufacturing excellence, who truly deserves the credit? Is it the company that first proves the concept, the company that scales it, the country that builds the supply chain, or does innovation ultimately belong to everyone who contributes along the way? I'm genuinely curious where you land on that, because reasonable people can disagree, and those discussions are always the most interesting. If you found yourself thinking differently about AI hardware by the end of this video than you did at the beginning, then we've accomplished exactly what I hoped. If you feel like sharing this video with someone who loves technology as much as you do, I'd really appreciate it, and if you decide to stay by subscribing, thank you. Every returning viewer makes these deep dives possible, and I never forget that this channel exists because people choose to spend a little of their time here. And there are countless technology stories unfolding right now that deserve far more attention than they're getting. And I look forward to exploring the next one together. Until then, thanks for watching, take care of yourself, and I'll see you in the next video.